Welcome to more substitution and inverse trig functions. So recall that we had figured out, for example, that the integral of 1 over 1 plus x squared dx was equal to tan inverse of x plus c. And then we had similar integrals for that resulted in secant inverse and sine inverse. So if we look at this integral I have here in our example, we'd have the integral of 2 over x squared plus 6x plus 13. We have a quadratic down below and just a constant up above, right? So we have a quadratic below. And a constant above. Then this lends itself towards trying to force that tan inverse formula. So we're going to complete the square. To try to force sorry, it's not updating. One moment. We're completing the square to try to force integral of 1 over 1 plus u squared du scenario. So let's go ahead and take x squared plus 6x plus 13. And our goal then is to write this as something squared plus some constant. And so since we just have x squared, we don't have a coefficient, we're going to have an x plus or minus some blank, and then squared, and then plus or minus some number. So in order to do this, let's just write this as x squared plus 6x, and then we'll have a plus blank. And then if we add something, we also have to subtract it, and then we'll still have our plus 13. So we want to keep the same polynomial essentially, just writing it in an alternative form. So to have a square, this winds up being twice. So we're going to divide this by 2 and then square it in order to get that. So when we complete the square, we take that middle coefficient, divide by 2, and square it to figure out what's missing. So this is 3 squared, or 9. So we are going to add a 9 here, and then we will subtract the 9 to counterbalance it. Now x squared plus 6x plus 9, we can factor. And then minus 9 plus 13 becomes plus 4. So this now x squared plus 6x plus 9 is actually x plus 3 squared. And then we have plus 4 on the end. So now we can go back to the integral. Where we had the integral of 2 over x squared plus 6x plus 13 dx. And we find that this is the same thing as taking the integral of 2 over, I'm going to rearrange this as 4 plus x plus 3 squared dx. Now we could use the rule that if we have 1 over a squared plus x squared, we know the integral, or we can do a little manipulation again. So if we pull our 2 out front, we have 1 over. Then if we factor a 4 from the denominator, we have 1 plus x plus 3 squared over 4 dx, or this becomes 1/2 times the integral of 1 over 1 plus, if we toss the 4 inside the square, it becomes 2 squared. So we have x plus 3 over 2 squared dx. At this point, we can go ahead and set u equal to our x plus 3 over 2. Then we get that du is equal to 1/2 dx, or in other words, which we actually have, or we could rewrite this as dx is equal to 2 times du. So again, our integral is equal to, we have 1/2 times the integral of 1 over 1 plus u squared times 2 du. If we pull out our 2, we're just looking at the integral of 1 over 1 plus u squared du, which winds up being tan inverse of u plus c. From there, we can go ahead and plug back in. So we are looking at tan inverse of, we had x plus 3 over 2 is our u. And then plus c. So again, I just did this for tan inverse. We can apply a similar rule for sine inverse and secant inverse as well, where you have to complete the square. You're more apt to see it for sine inverse since there's only one x involved in the integral. And you may need to complete the square and force the format 1 minus u squared inside of your square root. But this essentially is how we can use completing the square to get a particular format to show up so that we can then take the integral.